Once we know how to manipulate algebraic fractions, we can multiply fractions, divide fractions, add and subtract. The next level on is the inverse process. In other words, taking a fraction that's all one piece and breaking it apart, splitting it into simpler fractions that, in this case, add together or subtract to give the result. This is really helpful when we get to binomial expansion or integration for Year 2 A-level maths content, because we'll be able to make use of our simpler fractions and calculate the binomial expansion, or make use of our simpler fractions in order to integrate when the original big complicated fraction wouldn't be so easy to deal with. Let's start with this example. 18x over 2x plus 1 times x minus 4. This is the form that we would expect to get. And this is the most important thing to get your head around for partial fractions. When you look at a complicated fraction, you can generally figure out what the two simpler fractions will look like, roughly speaking. You can't tell what the numbers will be on the top, but you can tell what the denominators should be. So essentially, we pick up our clues from the denominator of the original fraction. If you're going to add two fractions together and the result will have a denominator of 2x add 1 times x minus 4, then it's a safe bet that your original fractions had denominators of 2x plus 1 and x minus 4. Once we've got that, all we need to do is add together the two fractions we've got on the right-hand side. So we're accepting that we don't yet know a and b, but we're expecting that given that we think there is a value for a and a value for b, we should be able to construct something here algebraically that lets us figure out what a and b have to be to make this work. So think of it like reverse engineering the values of a and b, because at some point we're going to find ourselves with an equation that must be true, and we'll be able to figure out what a and b have to be. This is what happens if we add the fractions on the right-hand side. In order to make the first fraction have the same denominator as the second one, and of course the same denominator as the fraction on the left, we need to multiply the top and bottom of a over 2x plus 1 by x minus 4. So you can think of this fraction as being a x minus 4 over 2x plus 1 times x minus 4. And a similar thing will happen with the other fraction. b over x minus 4 gets multiplied by 2x plus 1 over 2x plus 1. So it doesn't change its value, it's an equivalent fraction, but now it has the same denominator as the fraction it's being added to, and crucially, the same denominator as the fraction that we want it to be equal to. Now, if those two are identical, and notice here we're using the identity sign, that means these two things have to be not just equal for some values of x, like an equation, where maybe you look for the values of x that make it true, but an identity is something which is always true. A bit like x plus 1 in a bracket squared is identical to x squared plus 2x plus 1. That will be an example of an identity because you know it's always true for any value of x, and you can safely substitute one for the other if it helps you to solve an equation or something else. So in this case, we know these two things must be identical for all values of x. We can already see that the denominators are identical. They're written in exactly the same way, so it's obvious. Well, all we need then is for the numerators to also be identical. So we write that out as its own line, and we ignore the denominators from this point on. Here's where it gets a little bit clever. We could expand out the brackets, and that's a valid method to use here, to break it all apart and look closely at each piece in turn. Maybe look at where the x's come from on the left-hand side and where the x's come from on the right-hand side, because you know it should be the same number of x's. And you could look at the constant terms on each side and do the same thing. But there's quite a neat shortcut method to that. This is supposed to be true for any value of x, which means that it should be true when x is, let's say, 4. Why 4? Well, I looked carefully at what was going on here, and I thought to myself, if x was 4, that would quite conveniently make this bracket disappear. 4 minus 4 would be 0, and then the bit that's got a involved would disappear completely. And that means we don't just get an equation that is true involving a and b, which we would get for any value of x we like, but this particular value of x gives me an equation which is true involving a and b, but actually it doesn't have any a's in it. So it's an equation that only involves b, and that allows us to find the value of b. Now, once you've found the value of b, that will automatically make it easier to find the value of a. Just like with simultaneous equations, when you're halfway through and you've found the value of x, finding y is pretty straightforward. You substitute back into one of your two equations. In this case, we can just pick a value of x that we like and we'll generate an equation involving a and b. If we're clever though, we can do a similar trick here. We can say what would make this bracket 0? Because if we can make that bracket 0, this entire bit disappears and we're left with an equation that only involves a. So I've done that. I've made x equal to minus a half. And that means on the left we have 18 times minus a half, that's minus 9. On the right we'll have a times minus a half take away 4, that's minus 4.5, or minus 9 over 2. So we can rearrange and we find a equals 2. The final step is just to go back to the top where we had our a and b, the original identity, and replace them with 2 and 8. And we know now that the original fraction that we had can be split apart into those two separate simpler fractions. So in general, this is a useful pattern to have in your head. I wouldn't necessarily recommend trying to memorize this particular big messy piece of algebra, but try to look at it and look at the general structure involved. If you've got something on the bottom which is factorized, then you can break apart your fraction into different sections where each of the distinct factors is one of the denominators of your fraction. Now, although I haven't mentioned it here, this does presume that the fraction you're dealing with is a proper fraction, as opposed to an improper fraction. So it's not a top-heavy fraction. We'll look in detail at what that means more carefully for algebraic fractions later on, but in general, what this is telling you is if the denominator is quadratic, the numerator has to be no more than linear. So think of the highest power in the numerator and the highest power in the denominator to give you a sense of whether it's a proper or an improper fraction. So in this case, the one we've got on the screen, there's a cubic on the bottom. So the thing on the top is not allowed to be any more complicated than a quadratic. It could be a constant, it could be linear, it could be quadratic, but it's not allowed to be any more complicated than that. There are ways of dealing with them when they are, but we'll get to that when we do algebraic division. So we split this fraction in our last example. What I'd like you to do now, instead of trying to work out the values of a and b directly for a few questions, which you'll do in a moment, but start by asking yourself, how can we split these fractions? So look at each one in turn and have a think about that very first line of the problem. How would you decide a over what, b over what, and maybe in some cases c over what? What would the simpler fractions be? What's the general form that you're expecting your solution to be in? Pause the video, have a go at writing that down for each of these 4 fractions, and when you think you've got something that seems right, then continue watching and we'll see if we agree. Okay, for our first one, because we've got 2 distinct linear factors, we've got an x plus 1 and an x minus 9, I can break apart the fraction into these two. Something over x plus 1 adds something over x minus 9. The second one, we've got to be a little bit careful with. It can be broken apart into distinct linear factors, but at the moment it isn't quite. We've got x, and then we've got something quadratic, x squared minus 1. So be careful with that. That piece can be factorized. It's actually the difference of 2 squares. It's quite a nice one to factorize. We need x plus 1 times x minus 1, and that will give me x squared minus 1. So although it may not look like it when you first glance at it, it's more similar to the third one and to the example in blue than it is to the first of our questions. It's actually 3 linear factors rather than 2. So we should get a over x, b over x plus 1, and c over x minus 1. And of course, which of those you put where doesn't matter. Your a, b, and c may be a different way around, but as long as your denominators are the same as mine, then we're all good. For the next one, it might look like there's quite a complicated numerator here, but the denominator is more complicated. The numerator is quadratic, the denominator is cubic, so we're all good. These are all proper fractions, so we can safely apply these rules. This one looks like this. X add 2 for one of them, x add 3 for another one, and 5 minus 4x for the last one. They're all linear factors, they're all distinct, in other words different, so we can safely have 3 separate fractions with each of the 3 factors. The final one, there's just one thing you need to do here. You've got to factorize the quadratic on the bottom. And when it's in the correct form, factorized form, you'll be able to see that there are distinct linear factors, and you can break it apart in the same way. Now you should be able to have a go at a few questions from the book. I'd recommend questions 2, 4, and 7 from exercise 1D. But if you want a bit more practice, there's plenty more in that exercise that you should be able to have a go at, including some problem-solving questions for a bit more, a slightly different way of looking at some of these questions, help you understand them more deeply, and some exam-style questions later on as well. So we have a method that works when we have distinct linear factors in our denominator. But let's have a little look at an example where the linear factor in the denominator is a repeated factor. Let's try this one and see what happens. X over x plus 3 squared. In other words, the denominator is made from two linear factors, but they both happen to be the same, x plus 3. This is what you would expect. At least this is what I would have thought of when I first came across this topic. Well, we've got two linear factors. Why don't I deal with it the same way I would if it was x plus 3 times x plus 4? I'll have two separate fractions, each one over one of those linear factors. You might already be starting to see why this may be a problem, because the right-hand side could be simplified to give a fraction which has a linear denominator. Because, in fact, those two fractions already have a common denominator. And if it can be simplified to a fraction with a linear denominator, it cannot possibly be identical to our simplest fraction on the left-hand side, simplest as in it's already in its simplest form, because that fraction does not have a linear denominator. If we go through the process, though, of making the left and the right-hand sides have the same denominator, this will become even clearer, hopefully. We can multiply the top and bottom of a over x plus 3 by another x plus 3 bracket. And we do the same with b over x plus 3. Now we've got the same denominator on this side as we do on this side. And therefore we can just compare the numerators. But here's where we start to see more of a problem. Because x plus 3 is a factor of the entire numerator, a and b basically get pulled out as a common factor. And you can start to see that there's going to be no easy way to determine the value of a or b. Because well, if a was 7 and b was 2, this would be no different to a being 6 and b being 3. A plus b is basically one single constant. It'll be clearer if we attempt to continue the method that we used before. We pick a value for x. This should be true for any value of x, so let's pick one. And if I choose x equal to minus 3, that actually makes things cancel out. But it doesn't just make the a bits cancel out, and it doesn't just make the b bits cancel out. It actually makes everything on the right-hand side cancel out. And we're left with this, which hopefully causes you to pause and be concerned. It's a contradiction. And what it means in this context is that there are no values of a and b that you could choose to make this original claim valid. This was an assumption we made at the beginning, and it turns out it's not a valid assumption. It cannot be the same. We lead to a contradiction. You're going to be looking at proof by contradiction. This is essentially how it works. You start with an assumption that you think may be true, or even an assumption that you suspect may not be true, but you go through the process of what would this lead to, and if what it leads to is something which is patent nonsense, then your assumption must also have been nonsense. So it proves that that format can't work. But don't worry, because there's an alternative. Let's try this again, but this time I've got a different idea. We're going to have a over x plus 3 just like before, but we're going to have an additional copy of that repeated factor in the next fraction, b over x plus 3 squared. Now you might be thinking to yourself, well, what's the point? If we want to break it into simple fractions, why is a number over x plus 3 squared any better than x over x plus 3 squared? Well, it turns out a number rather than something linear is actually more helpful. When it comes to integration, we can quickly and easily integrate 5 over x plus 3 squared, for instance, but we cannot quickly and easily integrate x over x plus 3 squared. So it actually does make a difference. The fraction is still going to be simple enough to work with, and it's still going to be a beneficial process to follow. Let's see what happens with this. Of course, because b over x plus 3 squared already has the same denominator as the fraction on the left, we don't need to do anything with that one. But the a over x plus 3 gets multiplied top and bottom by another x plus 3 bracket. Now we compare our numerators. And again, we can go through the process of picking a value for x. I'm going to use x equals minus 3 again. and this time it's only the a part that cancels out and disappears, and we get b must equal -3. Brilliant. Now we can go back and try to find out a. There's no value of x that will make the b section cancel out because it doesn't have any x's next to it. But don't worry, sometimes there are nice values of x you can throw in that will nice and efficiently eliminate certain variables, but that's not always the case, and it doesn't really matter too much. If there's no nice value for x that you can put in, just make up some other value for x. Any value you put in will give you a valid equation linking a and b. And we've already found b, so it doesn't matter if our equation has both a and b in it. That's what we'll do here. I'm going to put in x equals 0. So although they won't completely cancel things out, if x is 0, then we'll get 3a plus b, and on this side we'll have a 0. So that's what we get, 3a plus b equals 0. And because we already know that b is -3, we can substitute that in, put this in here, rearrange, and we get a equals 1. So this is the new fact to make sense of. If we've got a fraction that has a repeated factor in the denominator, as long as we make sure we include that extra copy in our list of smaller fractions, simpler fractions that we break it into, it should still work. You'll notice in this example I've got ax plus b, which just appears on its own. So that gets broken in the same way. We just get something over ax plus b. And then for the repeated factor, we have that extra copy. We have the cx plus d and the cx plus d squared section, and that makes things work. Just like we did before, I want you to have a look at a few fractions, and not to work through the whole process, but just to see if you can write down how they will be split up. So they've all got some form of repeated factor in the denominator. I'd encourage you to pause at this point, have a go at each one, see if you can write down the correct format involving the capital AB, possibly A, B, C, maybe even a D, to show us the simpler fractions that we think it should be possible to convert these into. When you're ready, unpause and we'll compare our answers. All right, the first one has a single repeated root or a single repeated factor in its denominator, x plus 1 squared. So I'm going to have an x plus 1 and an x plus 1 squared. For the next one, there's an x, but there's also an x minus 4 and an x minus 4. So I'm going to have an x in my first fraction, an x minus 4 in my second one, and then an x minus 4 squared in my third one. For the next example, we have x plus 2 cubed. It's been repeated a lot. You might have just had a bit of a guess here. If you're not sure, see what happens when you work it through. And if you get a contradiction, then you've probably made a false assumption. But if it can work and if it seems consistent, then you've probably chosen a format that works. In this case, we have a single copy of x add 2, and then in the next fraction, a squared version of x add 2, and then in the final one, cubed. So we have a single x add 2, two of them multiplied together, and then three of them multiplied together in each of the three denominators. For the very last one, we've got three copies of one of our factors. We've got x cubed, and we also have another one thrown in there. So we're actually going to have four fractions in here: a over x, b over x squared, c over x cubed, and finally d over x minus 8. If you're happy with those, the next questions to try are already up on the screen. Exercise 1E, questions 1, 4, and 8 are a good starting point. Again, if you want more practice, try some of the simpler questions near the beginning of the exercise. And if you're feeling confident, pick out the problem-solving questions, the exam-style questions, maybe even the challenge questions that you find in this section. The last thing we're going to look at is a few examples more so that you've got a bit more detail of how you would work through this one at a time, finding your values of a and b, or a, b, and c. There are three different levels here, so you might recognize particularly the first two. If you can break apart a fraction into distinct linear factors, it's one form. If you can break them apart involving repeated factors, it's a different form. And then the last one in red, that's going to involve something a bit more sophisticated. Think about why it might be the odd one out. And the reason here is that the fraction you're looking at is top heavy. And that's still going to be doable using our partial fractions techniques, but it takes a little more careful thought, and it will give you a bit of a heads up in terms of what's coming up shortly with algebraic division, how we can break apart something like a polynomial, like this cubic expression on the top of the fraction, if we're dividing it by something simpler on the bottom. The first one, we're going to factorize the denominator to begin with. That's because the entire basis of partial fractions is built from the idea that if you have two fractions with different denominators, they can be added together by combining those denominators to give a common denominator. If the denominator we're looking at with this single fraction can be decomposed into separate factors, then there's a good chance we can find two separate fractions with those different factors as their denominators that add together to give this fraction. It's important also to notice for this one, we're looking at a proper algebraic fraction. In other words, the order of the top is linear, so it's a polynomial of order 1, is strictly less than the order of the bottom, which is quadratic, so it has order 2. So we say that 8 minus x over x times x plus 4 may be identical to some combination of fractions with denominators of x and x plus 4. The next step is to combine those two fractions on the right hand side. And you'll notice at this point, crucially, the denominators for the left hand side and the right hand side match perfectly. And if we want these two things to be identical, that means they're not just the same for certain values of x, but they are the same for any and all possible values of x. And if the denominators match, then the numerators must match as well. And what that means in practice is that once we know the denominators are the same, we can ignore them and focus on just the numerators. So we've got 8 minus x must be equivalent to a times x add 4 plus b times x. Once we've got that, there's a really useful trick that is probably the most common thing I will do when I'm dealing with partial fractions. There are a couple of different things you can do, and I'll demonstrate both, but this is probably the easiest trick for this standard format of partial fractions. We do what I think of as a savvy substitution. We think of a clever value of x that we can substitute into both sides of our identity and reduce everything down to something nice and simple. In this case, choosing x equals 0 is not just a good idea because it's easy to just get rid of anything where x appears, but crucially, the term involving b is multiplied by x. So if x is 0, b disappears from the equation. We get 8 minus nothing equals a lots of nothing add 4 plus b lots of nothing. Therefore, a is 2. We've got the value of a straight away. If we'd chosen a different value of x, then the equation we generate would still be just as true. We could have x equals 1, and that would give us 7 on the left, and then 5a plus b on the right. And 5a plus b is equal to 7, but then we'd have to come up with another value of x and generate another equation and then maybe solve simultaneously. What we're doing by choosing x equals 0 is allowing one of our two simultaneous equations to be so simple that it only involves one of the variables. And we can actually do the same thing. If you look carefully, we can find a suitable substitution for x that will make the term involving a cancel out. This is the bit involving a. Let's see if we can make that bracket equal to 0. So we set x equal to minus 4. On the left we get 12. On the right the a term cancels out. We get a times nothing. And then we get b times minus 4. Therefore we can find the value of b. And that means we can write our fraction now as 8 minus x over x times x plus 4 equals 2 over x plus negative 3 over x plus 4. I've just replaced a and b with the values that we found. And if you want to double check, it's fairly quick at this point to add the two fractions together and see if you get what you had at the beginning. Another nice way to verify is to pick a random number, preferably one that you've not already tried, something other than 0 and minus 4, and see what happens when you substitute it into the left hand side and into the right hand side. One thing to mention at this point, if you do try substituting in 0 or minus 4, you'll find something strange happens. The fraction is undefined. That's not a coincidence. It's precisely because those things are factors of the denominator that they turn out to be useful things to substitute into when we were finding terms that fit for the numerator.
If it feels a little bit strange using those values to find the a and b values initially, remember all we're doing at that point is focusing on the numerator of each fraction and saying we need these to match for any value of x. And if they match for any value, they will of course match for the two values that we wouldn't actually substitute into the fraction in the first place. But they will also match for all the other ones. So it's really a method for finding the a and b values, which will give us exactly the same a and b values as we get subbing anything else in, but more quickly and easily. There's only one other thing I would suggest here. It's probably a little bit nicer to bring out that minus sign and call it 2 over x take away 3 over x plus 4. It's not really essential, but if you've got an awkward fraction on the top of one of those fractions, for instance, add 7 over 2 over x add 4, then it can be a bit nicer to sort that out a bit, deal with your denominators and numerators so that you end up with a single fraction. It's a little more elegant. Let's look at the second one now. There's a difference here. We have a quadratic on the top instead of something linear, and yet it's still a proper algebraic fraction because on the bottom of the fraction we've got a cubic. So the order of the top is 2 and the order of the bottom is 3. So it's still, effectively, it's like a fraction like 3 over 4. You can't turn it into a mixed number. You can't divide 3 by 4 and get a whole number answer. So this is still going to break apart in a relatively similar way, but there's another important difference. When we factorize the bottom, as you can see, this one's pre-factorized for you, you'll notice that there's a repeated factor. We have x minus 3, and we have another x minus 3. And if it was 3 completely different factors, x minus 3, x plus 7 or something, we could split it into 3 different fractions, each of which has one of those factors as its denominator. But when you have a repeated factor, there's a slight difference in the way you set it up. And this is because if you attempted to make this work with b over x minus 3 plus c over x minus 3, well, those two things are basically the same as b plus c over x minus 3. So the whole thing would reduce down and it wouldn't give you enough flexibility. Essentially, we need 3 distinct constants that we're able to mess with and tweak and adjust in order to make this work. And if the format that we come up with only leaves us with 2 effectively different constants, then we're not going to be able to break apart the fraction. You don't need to worry too much about the ins and outs, but if you want to play around with it and try to see what happens if you come up with a different approach, then by all means do so. The method we're going to apply here is the same kind of thing we did before. So we need to add the fractions on the right and generate a common denominator. The common denominator on the right should perfectly match the denominator on the left. So you can see that the first fraction, a over x, needs multiplying by x minus 3 squared over x minus 3 squared. In other words, times the top by x minus 3 squared and times the bottom by x minus 3 squared. That way the denominator will match the one on the left hand side. For b, you need to multiply the top and bottom of that fraction by x and also by another x minus 3. And when we get to c, we just need to multiply the top and bottom by x. You'll notice also one slight time saver. I'm not writing out the denominator. I could, but I know what it would be. It will be x times x minus 3 squared, and more importantly, I know it will be the same on the left hand side and the right hand side. So it's not strictly necessary to write it out on both sides if all we're going to do is ignore it from now on. We're going to use the quadratic on the left and the quadratic on the right, and we're going to compare them and figure out what a, b, and c would have to be to make this work. Now we can do a similar thing to what we did before. We can think of a savvy substitution. Is there a value of x we could substitute in that would allow certain things in here to cancel out nicely? And x equals 0 works quite nicely again because x is a factor. In fact, x is a factor of both this bit and this bit. b times x minus 3 and c times x. So both of those will cancel out. And we're left with just minus 9 equals a times 9. So a is equal to negative 1. The next logical substitution to make is x equals 3. And in this case, if we set x equal to 3, we find we can cancel out the a bit because there's an x minus 3 bracket there. And we cancel out the b part again. And we're left with just the c component. and that means we can calculate c. Everything else disappears, cancels down, and we get c equals 1. But you might have noticed the problem here. There is a way to cancel out a and b. There is a way to cancel out b and c. There is no way to cancel out a and c without also cancelling out b. Anything that cancels c will cancel b, and anything that cancels a will cancel b. If you want to not cancel b, you have to not use 0 or 3. But if you don't use 0 or 3, you won't cancel out a and c. Well, this isn't as big a problem as you might think, because although these were the most efficient and lazy substitutions we could come up with, they are only 2 of an infinite number of perfectly valid substitutions. We can put any number we like in instead of x. And even if we get something that doesn't perfectly cancel out everything, even if it involves a and b and c, that's not a problem necessarily. Importantly, because we already know a and c. So even if we got an equation with a, b and c in it, it still doesn't stop us from finding the value of b. So let's try x equals 1. It's a nice, easy option. On the left-hand side, we have 1 squared, add 1 minus 9. And on the right-hand side, we will have 4a minus 2b and c. Well, if we put all that together, remember we can rearrange this and we can substitute in the values that we already have. We know what a is and we know what c is. So we can make use of those and simplify and solve for b. Now we've got the value of b. The last thing to do is to go back to our original fraction and rewrite with the appropriate values a, b and c in their appropriate places. The third example is a little bit different. The numerator has a cubic, a polynomial of order 3, and the denominator is a quadratic, a polynomial of order 2. So this one is most definitely a top-heavy fraction, an improper algebraic fraction. The first thing I would think about when looking at one of these is the kind of answer you would expect to get if you were to carry out the division that's implied by the fraction. If you start with something cubic and divide by something quadratic, what kind of answer should you get? The easiest way to make sense of this in your head is to think of the simplest cubic and the simplest quadratic you can. If you do x cubed and you divide it by x squared, you get x, which is linear. And that's true for any cubic and any quadratic. If you divide a cubic by a quadratic, you get something linear. In fact, if you divide anything of order, say 7, by something of order 3, you will get something of order 4 as your quotient, your result. There may be a remainder as well, but the bit that we're most interested in here is the quotient, the bit you get which doesn't have any division going on inside it. So this is the kind of thing we're going to end up with. If we're able to break apart a cubic divided by a quadratic, it should end up giving us something linear, which I've called ax plus b, and then the rest of it could then be broken down in the normal way, because the rest of it will be a proper fraction. That's the whole definition of algebraic division. You're taking something which is an improper fraction and you're rewriting it in a form that involves a polynomial, the quotient, plus a remainder over the divisor. In other words, something over, in this case, x minus 1. And that remainder must have a lower order than the divisor itself, because it's a proper fraction and the divisor is its denominator. So if the divisor is quadratic, then the remainder must be at most linear. We've got something linear over something quadratic, which is exactly the same as the very first example that we did back up here. So we can break it apart in the same way, and we'll get something like this. Let's see how this works. We can still add the 4 terms on the right-hand side. 2 of them don't look like fractions at all. We can think of ax plus b as being a single term, if you like, as I've done here, stick it in brackets, but we're going to multiply it by x and by x minus 1, because at the same time we're dividing it by x and x minus 1, so that all of those terms on the right share a common denominator, x minus 1. C gets multiplied by x minus 1, as well as being divided by x minus 1, and d will be multiplied by x over x. Then all the denominators match, and we can ignore the denominators and just look at the numerators. Now, how do we break this one apart? Well, we do the logical things. We try substituting in things that will make stuff cancel. There is a factor in here, there's an x that we can make use of, which multiplies by the ax plus b term, but also by the d term. So if we substitute that in, everything apart from c will cancel out. And that's what happens. We can find the value of c. The next logical thing to try is 1. If we substitute x equals 1 into our formula, it'll cancel out this bracket and this bracket, and we'll be able to find the value of d. We get -4. Then it gets a little messy. So there's nothing else we can substitute in that won't cancel out the thing that we're trying to find. We need to find a and b. So let's try substituting in a couple more values of x. We pick nice simple ones. If we've not already used 0 or 1, we would use those. And if not those, then the next logical options are -1, 2, things like that. So I'm subbing in -1 to see what we get. And as expected, we get something which involves a, b, c, and d. But remember, we already know c and d. We've got numbers for those. So wherever you see c or d, we can just replace them with the appropriate numbers. And when we perform the substitution, do a little bit of simplifying, we get 2a minus 2b equals 2. I won't simplify that, I'll leave it in that form for now, because if we're going to be solving it simultaneously in a minute, we don't know what the most appropriate form might be. The next thing we'll need to do is the same kind of thing again. Pick a value for x. There's no right or wrong answer here. Just choose a number that you are happy substituting into both sides and think you're less likely to make mistakes with. I've gone with 2, excitingly enough. And we end up with 4a plus 2b plus c plus 2d is equal to -1. That cancels down, simplifies a little bit as well. We get 4a plus 2b equals 4. Now you could at this point cancel down, write both of those in a more straightforward format, but in their current form, it's easy to see how we can solve those simultaneously anyway. You could do it with a calculator if you wanted, and if you do end up with 3 simultaneous equations in 3 unknowns, which is also possible with some of these depending on your method, then you might find it's a lot quicker to take advantage of your calculator, which I believe can work things out up to and including 4 simultaneous equations in 4 unknowns, which might be quite handy. But in this case, it's pretty easy to deal with using elimination. If you add the left-hand sides, you get 6a. If you add the right-hand sides, you get 6. So a is 1. If, on the other hand, you double the top one, or equivalently halve the bottom one, then you could subtract 1 from the other and you could find the value of a. Or you can use substitution once you know the value of b. Find the value of b. Anyway, whichever way around you do it, you should get a equals 1, b equals 0. And you can double check that they work by substituting them in. We get 2 times 1 take away nothing is 2, and 4 times 1 add nothing is 4. But that seems a little bit much. Those last 2 steps, they weren't particularly quick and simple. There were all sorts of little places where you might make a mistake. I certainly did. I made a couple of different mistakes when I was going through this the first time through. I had to keep going back and correct it. There's a lot of little things going on, and that's often the place where little mistakes can creep in and be hard to notice. There is an alternative method. The previous method felt a little bit clunky and slow towards the end, so this seems like a good opportunity to demonstrate the alternative. We still do the first couple of lines the same, but now we're going to see what happens if we use the comparing coefficients approach. This approach is essentially saying, if you've got a quadratic and I've got a quadratic, and we think they're identical for any and all values of x, then the number of x squareds needs to be the same, the number of x's needs to be the same, and the constants at the end need to be the same. It's exactly the same principle we're using here. We have a cubic, so we can compare in turn the x cubed terms, the x squared terms, the x terms, and the constants. We start by looking at the x cubed terms. And somehow I've just jumped to 1 equals a. Where did that come from? Well, let's have a look. On the left, the x cubed term is just 1x cubed. On the right, we can find an x cubed term by multiplying ax by x by x. And if you look carefully, you'll find that's the only place you can find an x cubed term. B is just a constant in that bracket. The most you can get from that is bx squared. If you were to expand that out, you get a bx squared and a bx times -1. You wouldn't get a bx cubed anywhere. And the c and d terms, they're just multiplied by something linear, so there's no way they're going to contribute anything to the x cubed terms. So we know straight away the value of a. We can do a similar thing with the x squared terms. If we look closely, we have a negative x squared on the left, and on the right hand side we need to be a little more careful here. There's a couple of ways to get an x squared term on the right. We can have ax times x times minus 1, but we can also have b times x times x. So if we put those together, and we notice that they are the only places you can get an x squared term, we can calculate b. Remember, although we have just an equation involving a and b, we already know a, so you can sub it in and find b directly. What about the x terms? Well, if we look for those, got a minus x on the left. On the right hand side, there's quite a few places you might get an x term, but not as many perhaps as you might think. In the big term at the beginning with the ax plus b, you'll notice that everything gets multiplied by x in there. So you won't have any constants coming out of that, but also there won't be much in the way of x terms. To get an x term, you would have to have b times x times minus 1. That's the only way it can happen. Because everything will be multiplied by x, you need everything else to be constant. So there'll be a minus bx squared. Sorry, minus bx. And then in addition to that, we'll have cx and we'll have dx. So we get a minus b, a c, and a d, balancing a minus 1. Remember, we know b, so we now have a link between c and d. Not enough on its own, but if we include the constant comparison, we can presumably find both c and d. And it turns out the constant terms, the only thing that provides a constant term is c. So minus 3 is the constant on the left. And if we do c times minus 1, that will give us a constant on the right. Nothing else provides a constant. Once you know c, you can go back up to the equation above and use it to find d. And we get the same result. We've got the same values for a, b, c, and d as we did before, but you might feel like this is a slightly more efficient approach in this particular case. In actual fact, neither of these, I think, is the very best way, but generally a blend of the two is the most efficient approach. So what I'd suggest is you either choose wise substitutions that will make things cancel out nicely, but then when you run out of nice things to substitute, then think about the coefficients involved to see if you can pull anything out usefully by looking at the x cubed terms on each side and so on. Very often the things that yield most easily to the savvy substitution alternative are the things that are hardest to get by comparing coefficients, and vice versa. So these two methods complement each other quite nicely. If you're feeling a little bit rusty on the entire process of partial fractions, if it feels like it's been a very long time since you learnt it, I highly recommend going back to chapter 1, trying a couple of mixed exercise questions on these, get your hand back in without having to think too hard about integration at the same time. Focus on each bit, then when you pull it together at the end, it'll feel fairly natural and easy to do.